Debugging Open RAN Interoperability Issues by Bob Stevens from Keysight. Is a senior solution architect. And he has been also a speaker at many of these IEEE conferences. He has worked in the past with Motorola, Nokia, to name a few. So we're going to hear from Bob about this specific debugging Open RAN interoperability. So I think this is probably the second talk around that area, right? All right, so I know Keysight, I have used Keysight product myself. So let's hear what, let me just open, 1 second. Let me just open your presentation, then I just, it should be it's a PowerPoint, right? Yeah. Let me just open it up. I want to make sure I project the right one. It's coming up. Okay, I opened it. Let me just share it. All right. Open RAN, debugging Open RAN. All right, all yours. Thanks. You just hit the arrow key.
Okay, I'm Bob Stevens. I'm from Keysight's Aerospace and Defense Government Solutions Group. I'm a 5G, 6G solutions architect, and thank you very much, Ashutosh and IEEE for having Keysight here. We believe that O-RAN is a very important factor in accelerating innovation and success for both 5G and 6G. Okay, so looking at the problem, as was mentioned earlier, I think Venki mentioned this, 5G networks in general are very complex. And if you overlay on top of that, the disaggregation of O-RAN, that creates some complex problems that you need to manage. But that also gives us some very interesting interfaces we can leverage. And it's those interfaces I'm going to talk about today with some use cases showing how we can leverage those interfaces to do very efficient and agile debugging. Because as was said before, O-RAN's a journey. Well, we need to be agile on that journey, be able to debug and take care of interoperability issues. All right, so if we look at some of the challenges here, the first one is that if you look at these networks, if you're not a telco operator, you're basically doing a private network. And for these private networks, there's some challenges that are unique for the private networks. That goes for DoD or any other applications, first responder networks, whatever it is. First one is we need to have high reliability. And so in terms of reliability, you'll hear a lot of the telco operators talk about 5 nines of reliability. That's 5 nines of past the decimal point. And if you have a pedestrian smartphone network, if you give best effort service most of the time, you hit 5 nines some of the time, that's okay. But for these networks, the expectation is 5 nines all the time. In addition to that, there's an expectation for resilience. These networks have to be resilient in terms of their RF operating environments and also from the network conditions. And then also higher performance. We expect very high performance for networks that we want them to be optimized. And so basically, when we look at that, there's a contradictory challenge though, and that contradictory challenge is that cycle time wise, private network operators and owners don't have entire departments of people that can go out and optimize the network like a telco operator can, right? So if you're a small operator and you're trying to create these 5G networks and you're trying to get all the benefits from the 5G network, what do? Well, the way to do that is to leverage runtime analytics on those O-RAN interfaces to make you more agile in terms of optimizing performance and getting results. So now, when you look at that, a lot of questions come up. There's a lot of pushback. Initially, people say, well, you know, if I'm using network slices on a commercial network, why do I have to test anything? Can't I just focus on my 5G applications? Or some people say, I'm using these COTS vendors that have tested their network elements for 5G and O-RAN. They're all compliant. Everything should work. Isn't integration just wasting time? Well, it turns out, and I think a lot of people in this room will realize as well, that when you hook up these networks, you don't always get the results you expect. Boxes that are supposed to be compatible, sometimes they don't even talk, right? And so you have to figure out what you're going to do about that. Once we figured that we need to do some debugging then the next question is, well, can't I use the log files that come with these boxes on the network? Why do I need to instrument anything? And the thing is, you'll quickly find that yourself swimming in a sea of log files and not being able to correlate them to anything. So being able to visualize 5G, visualize the RF, visualize the O-RAN protocol stack is very important for debugging. And then that takes us to, once we've done that and the network's functional, then performance testing. A lot of folks ask, well, you know, aren't there things baked into the standard, hybrid ARQ, automatic repeat requests, right? Codebook selection for MIMO and link adaptation. Don't these things just take care of business for us? Well, if you're doing remote telesurgery on a network, you're using network slices, would you just want to rely on HARC, or do you want to know that you've instrumented the network to know that you need to switch over to a redundant slice preemptively using some AIML technique? I would vote for the second one, right? Okay, so now what we're going to do is we're going to talk about using these interfaces. So this diagram here shows a high-level overview of the 5G O-RAN network. And starting from the right, we have the 5G core. If you have a core emulator where you can simulate all those network virtualization functions, you can actually do things like hardware and software in the loop to replace pieces of them as you migrate through the network. When we do a network slicing, it's important also to remember that there's subsegments of that slice. There's core slices at the core, there's transport pieces to the slice, and then there's the RAN pieces. And being able to instrument at each one of these points and then correlate them is important. So we have tools here that we can see as we move from right to left over here. We've got in the O-RAN network, when you look at the front haul, the mid haul, we can tap at those points. And then we have the RF that we can instrument as well. Taking a logical view of that same picture, what we can do here is we can actually implement either virtual taps or physical tap points and use something called a packet broker. A packet broker is basically a hardware accelerated filter for filtering packets on the network to stream those packets to analytics engines, and then having those analytics engines then be able to interact and look at attributes and key KPIs that they're looking at. We can actually correlate our application layer performance with the underlying KPIs. Okay, so that being said, now what we're going to do is we're going to go look quickly at 5 different use cases here. So we're going to first look at throughput, debugging throughput from RF through O-RAN, looking to see what performance looks like there. We're going to look at beamforming debugging, both in the context of the RU and also at scale for multi-user MIMO and massive MIMO. Then we'll look at O-RAN and energy efficiency management and how we can have the RIC factor into that. And then we're going to look at network slicing and looking at network slicing performance and how does the RIC factor into that. And then finally, we'll take a look at O-RAN timing. Okay, so let's first look at throughput. Okay, so you have all your O-RAN network elements, you connect them all up, the network goes on air, and you get all your UEs, your devices, your reduced capability, RedCap, IoT devices. You got to have this whole ensemble of devices on the network, and this happens. 44% blur. So what do you do next? Who do you call? If you had one of the major OEMs or a telco operator implement your network, you'd know where to go. But you created this network yourself. And so what you need to do is you need to figure out, well, where's the problem? Is it an RF problem or is it a network problem? Maybe for the RF environment I have here, 44% blur is the best I can do. But the question is, where do you start? How do you figure out what the next step is? Well, let's walk through that. So we'll start out by taking a look at RF. And looking at RF here, we can see, I'm not sure if everyone's familiar with constellation diagrams in the room here, but this is a constellation diagram showing the modulation scheme that's being used here. And so what we look at here is we can see, we can't tell if this is 256 QAM or 64 QAM, but we see there's a lot of noise there and we can't really distinguish what's happening. The other thing that you can see on the top left, there's something called channel coder bit errors. Channel coding, right, adds bits that are overhead to protect the data we're sending. And based on patterns and the algorithm for the channel coding, the channel decoder knows how to flip bits and correct bits that are in the wrong sequence. Well, we can see here the channel coder is working really hard. So on the surface, it looks like we might have an RF issue here, right? The other thing too is there's something called the channel impulse response in the top right. That looks asymmetric. Looks like it could potentially have some multipath here. So all the data here seems like it's lining up to say we might have an RF issue. But then if we look at another one of those bursts that's being transmitted, the PDSCH on the downlink, we see here, well, this constellation is 64 QAM, and this is clean as the Irish Spring. However, the channel decoder is still working just as hard on this one. So that raises the question, well, what's going on here, and why is it intermittent? Why are we still correcting all these bits? And then the third thing we look at here, we also look at the sync channel. The sync channel is kind of like the lighthouse beacon from the site. first thing the first thing the UE does on the downlink is it frequency locks to the downlink. And in this constellation, we expect to see, just like the top right one, we expect to see, this is QPSK, so we expect to see four pinpoint dots here. But we see there's frequency rotation. So this means the devices are going to have frequency here in the downlink. So all this seems to look like an RF issue. Well, if we continue on a little further, we look here to see, if we look at that burst we looked at it a minute ago, each of the transport blocks that's transmitted are made up of code blocks. And in this particular burst, we can see these red boxes. There are 3 code blocks that went into the transport block here. And so what we can see here is the reason that the constellation is a mess is because this light green stripe on the far right, that's where the DMRS, the pilots are in the PDSAH burst. And we can see on the left, the data is completely absent. Light gray scale there means there was energy, dark gray scale means there's no energy. And so the reason this CRC failure happened is because we were missing those DMRS tones, which are basically the reference symbols to help decode and do channel estimation training. So then if we look at that other constellation, it was cleaner. Well, this one only had one of the 3 code blocks failed. But in this case, what we can see here is we're again missing a complete symbol's worth of data there on that dark stripe that's on the right. So that's interesting. So now what we can do here is we can actually go in and shift the analysis to the ORAN piece. So now what we're doing is before we were looking totally at RF. Now what we're going to do is we're going to reuse the exact same set of tools, and we're going to go look at that front haul ORAN interface and decode the 5G protocol stack. Now the great thing about this is that we can do what I would refer to as correlated analytics. We're able to look at the 5G protocol stack and the ORAN protocol stack at the same time. And here we can see we're missing that energy again. To the right side on the left capture that you can see there's no energy in the gap there. And so then if we look on the right side, we can see here what we're doing is we're visualizing the ORAN protocol stack and looking at that same PCAP data. Now what we're seeing is we're seeing the control plane and user plane there. We can see the control plane shows no gap. The control plane says we should have been sending RBs there. But on the bottom part, you can see ORAN is telling us, well, hey, there's, we have a gap in energy there. So, and if we look at the top, we can see there's U-plane sequence number errors. So what this let us do is it let us go all the way from RF, debugging a problem that seemed like it was an RF problem, all the way down through ORAN, and it told us, well, what plane in the ORAN protocol stack the problem is in. Now, the way we modeled this was we actually took a network emulator unit and put it in between the DU and the CU. And so what we did here then was we were dropping packets to model an imperfect network. And so what we did here then is when we did that, then we used that same interface then to capture packets and look to see what we had in terms of the anomalies. And so, now the other interesting thing here is that we actually then took in with the exact same packet drop error rate, we took and reconfigured the 5G protocol stack. So in changing the 5G protocol stack to a different configuration, we can see that same packet drop error rate resulted in a 6% blur for the one configuration and 44% for the other one. So, we hear a lot about resilience and making 5G networks resilient. Well, this is what resilience looks like in terms of optimizing it and the way to do it. 5 minutes. Okay. So let's really quick look at beamforming. So in beamforming here, what we're doing is we're taking a DU emulator, driving an RU, and doing captures at the output. We're sub-6, but if you were at FR2, you could do this over the air as well. So what we're seeing here is we've got again, looking at that same ORAN traffic across the front haul, we can actually see the beam coefficients here. So we can look to see exactly what beam coefficients were sent across that air interface, across the front haul. Next, we can see here that we've got, we're only transmitting SSBs, and SSBs are 20 RB, so we can see those 20 RB SSB allocations there on this chart. So we see here then is we expect to see 8 beams, because we got 4 SSBs, 2 occasions per SSB, and we can see those 8 beams there. However, you can see in the arrows on the left side, the side lobes are much higher than we expect here. So this is a technique we could go through and we could debug and optimize the beamforming coefficients to see, is it a calibration issue in the RU, or is it a software issue for the beamforming coefficients? Now let's switch over to debugging beamforming at scale. Here what we're doing is we've got a core simulated here. The units under test here are the DU and the CU. And on the left side, we have something called an RU sim. The RU sim actually simulates RUs and UEs. And so what it does is it connects over that front haul interface to load the DU and the CU at scale. And so what we're doing here is we actually have a beamforming solution that's created over here by the DU. In the top right there, you can see the red circles are the spatial streams that are getting scheduled to the UE positions that are the blue circles. And once that beamforming solution is created, then it's sent over to the RU sim here, and the RU sim does the mapping from those spatial streams to the UEs. But what this lets us do is it lets us do a lot of debugging at scale with a lot of users and optimizing beamforming. Okay, ORAN and energy efficiency. We get very fine-grained control in the frame on an RB basis and also on a symbol basis in terms of what ORAN gives us. You could actually do things on every symbol if you want. And so what we have here is this is the 706 specification that specifies, okay, what measurements you have to make in terms of looking at energy efficiency. Note, one interesting thing to note here is that we've got receiver sensitivity as part of that. This is the block diagram for what we had set up here to make these measurements. And here again, now what we can do is we can look at the section IDs, and you can see here type 0 is idle, meaning don't transmit. And type 1 is normal transmit or receive. And so what we can do here is we have fine-grained control. So we can configure what's shown on the right there is the gray boxes are symbols and where we have inactivity. There shouldn't be any energy being transmitted. And you can see around the green stripe, which is a PDSCH, and the yellow stripes to the left, there's gaps around them. Well, that's because this is now configured to say if there's any activity in the slot, don't deactivate, just keep that slot active. But we could also, if we wanted to, say if there's no activity in the symbol, deactivate the symbol there as well. And so this gives us very fine-grained control for looking how to debug that. This is another thing that was done here, what the Keysight did with these companies that are listed here. What we did was we measured ORAN or DU and CU power efficiency using this configuration with virtualized DUs and CUs on the server here. And here's another thing that we've done with the RIC, where we've taken and we have a number of UEs that drop out over time. And then we have the RIC detecting that based on measurements and then optimizing and turning off the RU. We can either turn that off. We can lock the cell down in sleep mode and have an 80% power savings, or we can completely shut it off, but then you have to go through the init sequence again. Okay, and now real quick, let's look at network slicing. In this case, what we're doing is we're looking at network slicing metrics per the TS28554 KPIs. And what we're showing here is that we can use a combination of that same protocol analyzer at front haul to look at the PDU session establishment success rates. Now, you might wonder why not just use stats from the DU and the CU here? Well, the reason is for what I showed in the very first slide. You can look at other metrics that correlate with that if you use the protocol analyzer. Then likewise over here in that core sim, as I mentioned before, we have the virtualization functions here, so you can look at the AMF stats as well at the same time and correlate those. Now, if we add in the box to the left there, to the left of the RU is called the channel emulator. As was mentioned before, kind of like what the Coliseum guys were talking about, we have a channel emulator. So we have custom channel models here. So you can take an environment that you've never been in, using ray tracing, you can create a channel model, then you can run the RU through this and go through and make measurements with this UE simulator here that simulates thousands of devices. And then you can correlate the behavior there with what's happening on the network. Then you can add in the RIC. We have something called the RIC sim here, which it can actually model near real-time RIC, and you can look to see, you can check to see per the 28552, are you getting all of the advertised measurements you want to get for those measurement groups? And then you can see here that we can measure on a per slice basis as many slices are configured for PDU sessions that have been established. And then the last thing here real quick is timing. Timing is a very key aspect on the network. Looking at things like even MIMO. MIMO requires 63 nanosecond synchronization between the antenna streams. So what we're showing here is that we've got this time sync analyzer unit that can actually take and look at timing. When you've got a hub side router and a cell side router, you can look at time arrival error from the DU all the way out to the RU going through this network topology, but you can also compare timing between the RUs, which is very important to look at. And these are just some of the graphs you can look at here. This is showing how you do a full 333, 8275 conformance test using that same framework. And then this is showing it in an actual network or a test bed, how you can use optical taps to look at PTP convergence and timing with PTP. At the same time, you're looking at 5G timing, looking at using the 1 PPS trigger, looking at the first bit of the first symbol in the 5G frame, and there's a grandmaster that's driving timing for all those things. And I won't go over all this right now, but Keysight kind of coined the term E-plane. You got the user plane, the control plane, and the management plane. We coined the term E-plane. So we have E-plane tools for measuring energy here. And then for anyone who's interested, you can go through and you can look at the ORAN solutions at the end. So I see Ashutosh standing, so.
This is very interesting presentation. I had a question about, do you integrate that with a real 5G core? I mean, I see the 5G simulator, right?
Yeah.
But if you're part of the system is pure 5G.
You can actually, what you can do, you can. One of the interesting things is product was called Load Core. And so what you can do is you can have what we would call as hardware and software in the loop. So you can actually take different pieces, you can have your AMF simulated, but the UPF is yours. Or, you can mix and match that way. So that's a good question. It's another good debugging technique,
right?
Because you can slowly, incrementally in these test beds, add in those other pieces, right? Yeah.
And I know you have this breaking point. Again, I'm coming back to security.
Yeah.
So that can be also plugged into this if you want to emulate different kinds of threats.
Breaking perf, sci-perf, all those things, IX chariot. There's a lot of things you can do in looking at in terms of exercising and doing different attacks in terms of what's there. Yeah, so we have that as well.
Thank you.